All right, welcome. In this video, I want to talk about the median of medians algorithm. This is a heuristic used in the Quicksort and Quickselect algorithms as a means for selecting a good pivot. And standard ways for selecting a pivot may arise in selecting a bad pivot, like the minimum or the maximum element. But the median of medians heuristic is guaranteed to select a good pivot, and we'll prove that in a moment. But before we look at the actual heuristic and prove some properties about it, I want to talk a little bit about the history of this heuristic. Now, if you recall, the quicksort algorithm and the quickselect algorithm were invented in the 60s, in the early 60s. And so by the the early 70s, as I've got here, 1973, they were fairly well known within the computer science community. And the analysis of the algorithm was fairly well known as well, knowing that the worst case is in fact n squared. And despite that, it was also thought at the time, and still is, to be an efficient sorting algorithm. And so there was some curiosity amongst the community as to whether or not there was a good pivot selection mechanism that would guarantee that the worst case would also be n log n as opposed to the n squared. So you can imagine what happened is at some conference in 1973, maybe these members all were sort of sitting down around some coffee, musing about this or puzzling about this problem, and thought, hey, you know, we're a bunch of future Turing Award winners. Maybe we can put our minds together and come up with a way to prove this. So indeed, in fact, they did. And so maybe I'll mention each of these members in turn. So the first one here I've got is Manuel Blum. This is Manuel Blum here. Manuel Blum is a Venezuelan computer scientist. He has made contributions to complexity theory, a topic we'll look at in a future video, some applications to cryptography and program checking. And so for these contributions, he was awarded a Turing Award in 1995. He also has a large number of notable students that he was the mentor or the advisor for, some of whom have also won Turing Awards. So he's made a contribution, and also some of his academic offspring have made similar contributions. Next, I have Robert Floyd. Robert Floyd is well known for a few algorithms, the Floyd-Warshall algorithm most notably. Robert Floyd was awarded the Turing Award again for his contributions in 1978. He did a lot of work in graph algorithms and also on parsing. And unfortunately, he passed away in 2001. Another researcher we have here, Von Pratt, he's on the side here. Von also made major contributions to various areas, search algorithms, sorting algorithms. He made contributions to primality testing. He unfortunately was not awarded a Turing Award. So out of these 5 individuals, all making very good contributions, he's the only one who was not awarded an award for that, although maybe partly because he did not practice computer science as much as these others did. Another researcher here, a little bit later awarded in 2002, Ron Rivest. Some of you may already know who Ron Rivest is. If you're familiar with the RSA crypto system, he's the R in the RSA crypto system, and he was awarded, along with his other 2 co-authors, the Turing Award in 2002 for the invention of the RSA quick crypto system. The RSA crypto system, of course, being the standard crypto system used in most of the world, at the moment at least, until we switch over to a post-quantum crypto system, which will probably happen very soon. And then finally, the last individual here on my list is Robert Tarjan. And Robert Tarjan, also a computer scientist, mathematician, awarded a Turing Award. He has worked in a number of different areas, but was also, famously the co-inventor of a couple of data structures you may have encountered, one being splay trees and the other being Fibonacci heaps. And again, he was awarded for some of his contributions. So again, all five of these individuals are somewhat giants in computer science, and together they were able to come up with this procedure for finding a good pivot in theta n operations, and they did this again in 1973. So we're going to review this procedure, the median of medians procedure. And before we do, it's commonly called medians of medians. It's also sometimes known as the BFPRT algorithm, named after them. But we're going to look at two important properties of this algorithm. One is that it guarantees to give us a good pivot. Now, what counts as a good pivot is up in the air, but according to this heuristic, it's guaranteed to give us a pivot that its rank will be between 30% and 70% of our entire list. So if our list is of size n, meaning that we're guaranteed not to pick a pivot in the bottom 30% near the minimum, or the top 30% near the maximum, meaning we're guaranteed to get one in the middle, in that middle 40% that is left over. And that we're hoping is good enough for us to get our n log n runtime. And again, I've got that stated here. Indeed, that is good enough to get a good n log n runtime for our quick sort, or specifically for our quick select, our big theta that we're looking for. So let's take a look here at the algorithm itself. Now the algorithm, remember, the heuristic here is just for selecting the pivot. However, it's kind of interesting. It's got a couple different calls in it to other subroutines that we're going to use. Specifically, we're going to call a subroutine called select, and we're also going to call a subroutine called quick select. Now these are different, of course. The subroutine for select is just a brute force select procedure, and we're only going to apply it to small lists. And so it's brute force, we're only going to apply it to small lists, so we're going to assume it takes a constant amount of time because we're only applying it to small lists. In addition, though, we are going to make a call to quick select. So this actually causes median of medians to be a recursive algorithm. So we're assuming, at least on the base level here, we're going to call median of medians as our first step in a quick select call. Our initial quick select call needs to find a pivot, so we call median of medians, but then median of medians down here is going to call quick select again, which in turn inside it will call median of medians. So there actually is a recursive structure for median of medians. However, it's sort of hidden or smuggled inside this extra call to quick select. So I'll try and make that clear as we go. Now this algorithm, how it actually works now is, well, we have a first early termination call. If the list is small enough, we just brute force it. If it's not small enough, meaning it's at least the size of 5, then we're going to go about and carry out this next sequence of steps. Starting with an empty list, we're going to fill this list in M one at a time by selecting medians of the list, of the larger list that we're looking at. But we're going to look at the larger list in chunks of size 5. So we'll see here, let's just for the moment assume our I is 0, it makes it easy. We'll go from index 1 to 5. From index 1 to 5, what we're going to do is select out the rank 3 element, meaning find the element out of those 5 elements that's the median element. Okay, so we select the median of those 5 elements and we just add it into our list. So after this for loop, we will have filled up our list M with some number of medians. It looks like about n over 5 medians of 5 chunks at a time, five elements at a time. So we fill those all up into this list M, And then we call Quickselect to select the actual median out of that smaller set that we've created. Let's look at that in a little bit more detail over here now. So what we can look at here, imagine that we have our list A. Our list A here is going to be our initial list with all of the elements in it. And here I've drawn it sort of long enough to suggest, okay, we're in the recursive case. So the first thing we're going to do is we're going to take these first 5 elements and we're going to brute force figure out what the median element, and I'm just sort of assuming it's this middle one here, but we're going to brute force it and we're going to copy it down here. Now up here again, well, maybe it was a different one that was in the median location. Now we copy that one down, and again we're going 5 at a time. Each time we're brute forcing and copying the median down into this list n. Now notice that if our initial list is of size n, since we're dividing them into groups of 5 here, we're going to end up with a list of size n over 5, assuming our original n was divisible by 5. I'm going to ignore some floors or ceilings for the moment. So then, the way the algorithm proceeds, the for loop fills up this list with m, and then we call Quickselect to pick out the actual median here. So we find the actual middle element, and this is the one that we're going to use as our pivot in our Quickselect algorithm. So there's a couple things that we want to argue about this property, or about this particular value that we've selected. One, remember, is that we want to argue that it's good, whatever that means, okay? And then 2, we want to prove that. We want to prove that because we've selected a good pivot, we can get our runtime that we're looking for, our n log n. All right, so I do want to argue that this value here, this pivot that we've selected, is good. And by good, I want to say that I mean that it's greater than or equal to 3n over 10 values. And so the way I'm going to argue that is, first of all, let's just look here. We notice that by selecting the median out here, we know, and I'm going to assume we've sort of sorted this list here. That's probably not how we selected the median. We didn't actually sort it, but let's assume for our argument that it was sorted, that all these elements are less than it, and all these elements are greater than it. So at least at the moment, we can argue that this value that I've selected here must be greater than or equal to this many other elements. How many elements are there? Well, if there are n over 5 elements in the whole list, and we're greater than about half of them, again, I'm ignoring a floor or ceiling here, maybe ignoring a +1 or a -1 here. But if we had n over 5 original elements, then we might end up here with n over 10 elements that we know were greater than. Already that's pretty good, but it's not here where we want it. We want to say 3n over 10. So already we've confirmed that this median element that we've selected must be at least as good as, or must be at least 10% of the way up from the minimum element, okay? Now the key here is that each one of these elements, remember that we added into M here, we selected it by being the median element of some group of 5, which means there are 2 other elements here that are less than this element, and that's true for each of them. There are 2 other elements less for all of these. So instead of getting this 1n over 10, because we selected each of these to be medians, we're actually greater than or equal to 3n over 10 different elements of the original list. Now we can do the same thing on the other side. We notice this median element must be less than or equal to all these elements here, and again those were n over 10, but each one of those was less than 2 other elements as well. So again, the total number of elements that we are less than or equal to must be 3n over 10 as well. So here I've done that sort of pictorially, but we can actually argue that as well, sort of verbally, with a proof. So here I've just got a simple lemma trying to establish this for us. So my lemma says the median of median procedure returns a pivot that is greater than and less than at least 3n over 10 elements. So let's just go through the points one at a time. We did it visually, but let's argue it now verbally. So the list consists of and the list M rather consists of n over 5 medians of lists of size 5. Well, that's how we established it. That's how we built that list, so we know that's true. We know each of these medians is greater than at least 2 elements in the list and less than at least 2 elements in the list. That's basically just the definition of what it is to be a median. We know that Quickselect, when we make our Quickselect call, will return the true median of medians. So we now pass M, the list M, into Quickselect and ask for the median. So we know there's no error there. It gives us the correct one. So this true median of medians must be greater than, and again, less than, n over 5 over 2, or n over 2 elements of M. Again, each one of those was, since each one of those was greater than or less than 2 other elements, then it means that our true median that we've selected here must be greater than, and again less than, at least 3n over 10 elements of the original list. And so that gives us our 30% kind of buffer here. And again, what that sort of means for us here is that if we have our list here like this, and we're able to sort of draw these lines, this is my 3n over 10, this is my 7n over 10, then I'm always picking a pivot in this range, and we're hoping, or we're calling this a good range, and these ones out here are bad. Okay, and again, that's maybe not that bad. We've got 30% out here, we got 30% out here. That leaves us with 40% in here. That sounds like it's probably going to be good. But it remains for us to prove that it's good, prove and show that this is going to be indeed n log n. So actually, in order to establish this, I'm going to consider not the quick sort algorithm, but instead the quick select algorithm that we're sort of building here with our median of medians. And again, it was a constant in our standard case. But what we want to do here is consider what's going to happen here in our recursive case. And remember, there's actually going to be 2 recursive calls that we're going to be making. Now, one of the recursive calls is going to be in our median of medians. In our median of medians, we call Quickselect, and we called it on a list of size about 1/5, and I'm going to ignore my floors for the moment here. But then, when we're done, now remember, we just said that if we had our list here, our pivot is either going to, well, let's for the moment assume the pivot we've selected is here. Let's say it's right at that 70% mark that we know. We know it's going to be between the 70 and 30% mark, but let's say we got as bad as we could. Remember, we might want to do a worst case analysis here. So the worst pivot we could get splits it into these 2 sets, where one side is 30% and the other side is 70%. Now, if this is the worst we can divide it, then the worst is to recurse on the big side. So if we have to run Quickselect now on the larger side, that's a recursive call as well of size, let's make it clear, 7n over 10. Okay, and we still have to do the pivot operation. Okay, now here some of you might think, why have I selected n, n less than or equal to 1 or n equals 1? Well, honestly, usually the constant value that we select here is not going to matter very much, but based on how we've sort of set things up, it might make sense for us to change this up to 5. Okay, because we said, well, if it was less than 5, we're just going to brute force it anyways. And again, this is sort of why it doesn't really matter what constant we have here. If we really wanted, we said, hey, well, we could brute force it all the way up to 500 and only worry about it when we get above 500. Well, that's maybe a little too aggressive, but in most recursive implementations, our cutoff point is usually a little bit higher than just 1. Okay. Now I wrote 1 for our recursive analysis because where this number does not matter in the end for our theta bound. The theta bound is going to be exactly the same whether this was 1, 5, 500, or 5,000 if we want. They're all going to give us the same theta bound. What it means is we do want to take a look at this. Can we prove a good theta bound on this? If we want to prove a good theta bound on it, we need to have a guess for the theta bound. Now, again, we might use one of our techniques to come up with a guess here, but the main technique for guessing has always been that, just guessing if we want to guess. So our goal here is in our quick select, we want to show that it has a specific runtime. Our worst case runtime for Quickselect already was n squared. So we probably, showing that's easy. We've already shown the worst case is n squared. So maybe we want to be ambitious and say, well, hopefully it's theta n. Our goal is to show that our Quickselect, when we use median and medians, is theta n. And if that's true, if our Quickselect with median and medians is theta n, then that means that our Quicksort using median and medians would be n log n, which was sort of the goal the whole time. So this is what we want to prove. Let's see if we can prove it. So I'm gonna set up a theorem here. T of n is less than or equal to b times n for n greater than or equal to n naught. And again, maybe I'll just write my t of n over here that we had. It was kind of a weird one. It was t of n over 5 plus t of 7n over 10 plus dn. Okay. All right. Let's go ahead. Let's do our base. I'm going to try n equals 1 for my base. We have t of 1, which we're going to say is c, is less than or equal to b times 1, which is just b. So it looks like as long as I select a b large enough, greater than or equal to c, then I'm good. So let's try our inductive hypothesis. So I'm going to, again, assume what I'm trying to prove. So rewriting my theorem, tk is less than or equal to dk, but for my restricted values of k here. Okay, and so now I can proceed to my inductive step. Okay, so starting off our inductive step, we're going to again copy down just the definition here. And our goal here is to eliminate our recursive terms by applying our inductive hypothesis. And we actually have two places we want to apply it here now. One for k equals n over 5. So this term we'll replace with b times n over 5. And then again here for this term, which is 7n over 10. So we're going to get b times 7n over 10 plus our dn. And maybe making sure that we are doing things right here, let's gather our terms together. So adding these two together, well, this is, let's, be careful, this is going to be 2/10. This is 7/10. So it looks like we're going to get 9/10 of a bn plus a dn. And we wanted to show that this is less than or equal to, looking up above here, bn. So we might say, well, remember this last step is our leap of faith. This is the one where we want to make sure we can do this. Is this true? Well, usually we had some kind of minus term here to cancel out with our plus term, and we don't have that here. So what can we do? Well, luckily here we might notice that we don't actually have a full bn here. We only have 9/10 of a bn. And because of that, if our d is small enough, more importantly, if our d well, let's make it this way. If our dn is less than or equal to 1 over 10 bn, then adding these two together will be less than a whole bn. So, well, I'll cancel my n's here. It looks like my b needs to be greater than or equal to 10d. So that's another condition on this. And so I can now just say, okay, let my b be equal to, and again, we'll do the max of c and 10d, and then we can say, so by induction, what did we show? We showed that t of n was less than or equal to b times n for all n greater than or equal to 1. And we're done. And there is a key here. Why did this proof work out for us? This proof worked out for us because our n over 5 plus our 7/10 added up to something less than 1. Okay. Now, some of you might think, well, hey, this was a nice heuristic, but why did we split things into 5s? Why didn't we split it into 3? Couldn't we have done it with 3? Well, I haven't done the math with myself, but my expectation is that when you added these two numbers together, you would get a 1/3 here. and you would get something more than 7/10 here, because splitting it into threes is not going to give us that 30% margin that we proved in the last theorem. So those two numbers added together added up to something greater than 1. And since it added up to something greater than 1, this proof doesn't work, and so we don't actually get our order n runtime that we want. So we can't run median and medians with just blocks of 3. We can run it with blocks of 5. We just proved that worked. In fact, if we wanted, we could probably run it with blocks of 7, and that would give us a better squeeze. Instead of 70% here, we might get it down to, I don't know, 60% or 50% or something. I don't know. I haven't done the math with that, but go ahead and use an exercise if you like. See what happens. See what the fraction you can guarantee if you increase yourself to 7 elements instead of 5. But again, in that exercise, if you want, go through your proof here and you'll see that you're still going to get theta n. Okay, theta n. And one key reason is it should be very, very clear here that this term is in omega of n. There's no way we're gonna be able to make it less than n, no matter what we change these two terms to. And the reason is this term all by itself is in omega of n. Okay, so another way of saying that, say we want to prove t of n is greater than or equal to d times n, we're done. We already know it's greater than or equal to d times n because these are positive terms. So that's sufficient, remember, for our big omega of n proof. Okay. So, all right, so a few takeaways here for our median of medians algorithm. The first is that by running it, we actually guarantee we pick a pivot between 30% and 70%, which is good, because what that means is if we then use that pivot selection algorithm for Quickselect or for Quicksort, then we're guaranteed to get that nice pivot every time, and we're guaranteed to get that asymptotic runtime in the worst case that we desire. So that means that our Quickselect worst case would be order n, and our Quicksort worst case would be n log n. Now, this all sounds really great. So it sounds like something we would probably want to use all the time. Unfortunately, what we are doing here is we are sweeping something under the rug, and remember, when we deal with these thetas here, we are sweeping something under the rug. So when I said this is theta n, I really mean it's less than or equal to some d times n. And the one thing we haven't talked about here is how the median of medians algorithm affects d. Our d gets really big, okay, or a lot bigger. And since this constant out front gets bigger, it means in a lot of implementations, it's actually slower to run median and medians. You spend a lot of time, finding perfect medians or perfect pivots that you're actually wasting time that you should have just been spending on sorting your list or selecting the element you're looking for. And so what that means is often we actually don't use the median of medians algorithm. We'll use just the standard randomized quicksort is more likely what we're going to use. With that said, there is one version of quicksort that uses median of medians, and it's got a different name. It's called introsort, meant for introspective sort. And the way introsort works is it actually just does randomized quicksort unless it detects, it keeps track as it's going down. If it detects as it's recursing that it keeps making bad choices of pivots, it stops itself and it starts running median of medians. So the idea there is we avoid this nasty D overhead most of the time. As long as we're randomly picking good pivots, great, but if ever we pick a pivot that we notice is bad, we stop and we go and we run the expensive algorithm to get a good pivot. And it turns out that this version, this introsort, is a good efficient version that does guarantee you an ed log n final runtime or worst case runtime. And interestingly enough, introsort is used in the C++ standard template library, at least it was originally, as the primary sorting procedure for that library. All right, I think that brings me to the end of the things I want to talk about in terms of both the median of medians and the quicksort and quickselect algorithms. In my next video, I want to take a look at another tool for doing recursive analysis called the master theorem. And it's going to give us a nice quick way to look at a whole bunch of different recurrence relations and come to a quick conclusion about their asymptotic runtime, their big theta bounds. So thanks for watching, and we'll see you in the next video.